Good afternoon, all of you. In the previous class, we studied about spontaneity. We spoke about the definition and we told also about some conditions for a process or a reaction to be spontaneous or not. And towards the end of the class, we spoke about few examples where the enthalpy change was not a factor for spontaneity. In case of ice, we told the heat is being accepted by the system and still it becomes spontaneous. So there was one driving force we were actually unknown about in case of spontaneity, or there was one driving force which we were not aware about in a spontaneous process. So continuing this question about the driving force about spontaneity, we are continuing to a new topic which is entropy and spontaneity. So this is a new term we are introducing now, which is entropy. So first we will see what is entropy and we will see how it is related to spontaneity. So this is an example which is given in your textbook. So it's a big container containing two gases. I have split the container into two halves, and in one side I have taken one particular gas named A, and in the other side I have taken gas B. And for example, I am trying to take a sample from this side. So I put a hole here and I am trying to take a sample from this side. Then which gas will I get? Obviously, I will get the sample of gas A. And this side, if I make a hole and if I try to take a sample from this side, I will get the sample B only. So this is the initial condition. So at this point, I am removing the partition between these two gases. So when I remove the partition between these two gases, what happens or what will be the change happening there? They are not solids. So if they were solids, if I remove the partition also, they will stand like this only. But they are gases. So when they are gas particles, they will move and they will mix up. So that's the change happening here. And did I put any extra effort to make them mix or to make them move? No. So I can tell it is a spontaneous process. So suddenly when I removed the partition between the container, then they started moving and they mixed each other. So without any external force, they mixed up. So I can tell it's a spontaneous process. One more fact is, if I try to collect a sample from this side now, am I sure of getting sample A? No, I might get sample B also. And this side if I am collecting, am I sure of getting sample B? No, I might get sample A also. So it is in a disordered form now. In this case, I was sure of getting sample A from this side and sample B from this side. But now, after the spontaneous process, I am not sure of getting sample A and sample B from their respective sides. So I can tell initially it was in an ordered form and now it is in a disorder. So the disorder of this system increased, and this disorder of the system is being measured by the term entropy, or this disorder is known as the entropy of this system, and that particular entropy is the driving force of our spontaneity what we were searching for. So initially we were searching for a factor of spontaneity, and yesterday we told it is not only the enthalpy or not only the energy which is responsible for the spontaneity, and one more factor was there which allowed the process to be spontaneous, and we were unknown to that. So now we can tell this disorder or this distraction in the system which is known as entropy is the factor for spontaneity. So as the disorder in the system increases, entropy also increases. Hence, the condition for spontaneity also increases. So yesterday we told this example of ice melting, and there we told energy is not the factor. But if you see closely, when the solid particle is converted to a liquid particle, what happens? Where there is increase in entropy or decrease in entropy. This is how a solid particle and solid atoms stay inside, and this is how the liquid stay. And what do you think? In which of them they will have more disorder or more entropy? Obviously, it will be in the liquid form. So in this place, the particles are very close to each other, they can't barely move. But in this case, liquids are more free to move. So there, the entropy or the disorder is more. They are more disordered, they can move freely. So hence we can tell, in this case also, entropy was increasing. It was getting converted from a solid state to a liquid state. Hence, entropy increased. And that increase in the entropy was the reason for that spontaneous process. So energy was not the factor, but the spontaneity was because of the entropy which was forming there. So these are the two factors for spontaneity. One, which we discussed earlier, is the decrease in energy, and now we tell the next factor, which is entropy. So entropy is nothing but the degree of disorder or randomness in the system. So for a system to be spontaneous, either it should reduce energy or it should have more entropy. Then we can tell the process is spontaneous. So combiningly, decrease in energy or entropy or increase in entropy will result in spontaneity. The greater the disorder in a system, the higher is the entropy. As we told, if disorder is more or when the particles are very free to move, then we can tell the entropy is also more. As far as the chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactant to the products. So as far as the reaction is concerned, reaction is nothing but reactants giving product. So in this place, if they are having very orderly arrangement and finally when the product is formed, so we have taken an example of ice cube. So the reactant was the ice cube and the product was the liquid water. There the entropy increased. In the liquid phase, the particles were free to move. So we can tell in this reaction or in the reaction of ice cube to water, entropy increased. So in any reaction, we can tell entropy like that only. We have to check the reactants, whether they are free to move, whether their entropy is high or low, and then we have to see the products where what is the condition of entropy in that side. So if the entropy is more to the product side, then we can tell it's a spontaneous process. So in case of solid, liquid and gas, solid are having very less entropy than the liquids than that of gas. Gaseous particles are very free to move and they will have more entropy. As they are very free to move, the disorder is more, hence entropy will be more. So in a reaction, if the reactant is solid and it is converted to liquid or gaseous form, we can tell it's an increase in entropy or one condition of spontaneity is satisfied. And if liquid is converted to solid or if gas is converted to solid or liquid in a reaction, we can tell the entropy of that reactant is decreasing. Hence in that particular reaction, it is not showing a condition for spontaneity. Entropy is a state function. It does not depend upon the path. So whenever heat is added to the system, it increases molecular motion. In any molecule, when we increase heat, it increases the molecular motion as we are providing energy and causing increased randomness in the system. So this you have learned from earlier classes. When you heat something, the molecules inside that particular substance will move faster or increase in the motion will happen. So hence that will increase the randomness and hence it will increase the entropy. So that's why we can tell heat is a factor for entropy. So distribution of heat also depend on the temperature at which the heat is added to the system. A system at higher temperature has higher randomness already in it than one with lower temperature. We told that heat is a factor for randomness and hence entropy, but it also depends on the temperature of the system. So when we provide or distribute heat to a system, we should also consider the temperature at which the heat is added. So change in entropy also depend on two factors, which are temperature and heat. We will see how it is. So we are considering two systems, S1 and S2, where one of the system is having lower temperature and one of the system is having higher temperature. And we are providing equal amount of heat to both of the systems. So it is not about temperature I am telling. So one is already at lower temperature, another at the higher temperature. So in this place the entropy will be at a higher range, and here the entropy is at a lower range as it is having lower temperature. And in this condition we are providing same amount of heat to both the systems. So both the system same amount of heat, but the difference will be in entropy, because these are already at a higher temperature, and if we provide heat also there will not be much change in the entropy. But in a lower temperature system, when we provide a particular amount of heat, the entropy change will be more. So entropy change will be more in this case than that of this case. So change in entropy is more in lower temperature. So this we can tell that change in entropy is inversely proportional to the temperature. So when the temperature is more, the change in entropy will be less. We are not speaking about entropy, but we are speaking about change in entropy. So change in entropy by applying a particular amount of heat will be lesser for a higher temperature system. For a lower temperature system, the change in entropy will be more with the same amount of heat. Hence we can tell change in entropy, we are not telling about entropy, you should be clear about that. We are telling about change in entropy is inversely proportional to the temperature. So for an equation for a reversible reaction, change in entropy is equal to Q by T. So Q is the heat change and T is the temperature. So it is proportional to heat but not temperature. The total entropy change for a system and surrounding for a spontaneous process is S total is equal to delta S system plus surrounding. Usually when we calculated the thermodynamics terms, we were speaking about just the system. But in case of entropy, we need to consider the entropy change of the system and even the surrounding, and we need to calculate whether the entropy change happening in the system is same as that of the surrounding. And if we consider both of them only, we can get the total entropy change. And in this reaction, one of them will be positive and one of them will be negative, as it is comparison of system and surrounding. So when the total of this becomes a positive value, so any of them should have a bigger positive value, then the total will become in a positive value. So the entropy, the total entropy should have a positive value or greater than 0. So when the total entropy is more than 0 or when we get a positive value, then we can tell that particular system is favorable for spontaneity. So when the S total becomes a positive value, then the entropy is favorable for spontaneity. So when entropy increases, the chance for spontaneity increases. When a system is in equilibrium, the entropy is maximum and the change in entropy is 0. So how is that? So when we consider a reaction, when it reaches equilibrium, the entropy of the reactant will be high and the product also will have a higher entropy. So both the entropies will reach a very high value and that will be the maximum. But the entropy change, if you see, Both of them are of same entropy and the entropy change will be 0. So this is the case of equilibrium. At an equilibrium process, the entropy of the system will reach at a higher value or a maximum value, but the entropy change will be 0. So entropy for a spontaneous process increase till it reaches a maximum, and at equilibrium the change in entropy is 0. So entropy, if it is a spontaneous process, it will increase and increase, it will reach a maximum when it reaches equilibrium, and at particular equilibrium the entropy change between them is 0. So since entropy is a state function, whether it is reversible process and if it is a irreversible process, the equation will be same, which is delta S system will be Q system in a reversible process by T. So it will have a value for reversible and irreversible process. The delta S or the entropy change will have a value if it is a reversible or an irreversible process. But in case of delta U, we have seen for a reversible and irreversible expansion of a ideal gas under isothermal condition, this we have dealt earlier in the classes, and we have found the value for this was delta U is equal to 0. So the internal energy was equal to, or the difference in internal energy was equal to 0, but the S total, that is delta surrounding plus delta system, is not 0 for irreversible process. So irreversible process and reversible process, we can differentiate them with respect to S total. But the delta U or change in internal energy is equal to 0 for reversible and irreversible process. And when you tell about reversible process, you should remember that in a reversible process, the system stays with the surrounding in equilibrium. So equilibrium is the condition for reversible process, and at equilibrium we told delta S is equal to 0. So in reversible process, delta S was equal to 0, but in case of irreversible process it is not 0. So we can differentiate with the help of entropy. We can differentiate the irreversible and reversible process with help of entropy, but that is not possible by delta U, as it is 0 in case of reversible and irreversible process, but entropy, it is not 0 for irreversible but 0 for reversible. Thus, delta U does not discriminate between reversible and irreversible process, because both the cases it is having a value of 0. But in case of entropy, it is having 0 value for one process, and in another process it is not having the value of 0. So discrimination of reversible and irreversible process becomes an application for entropy. So I hope you all are clear with what is entropy and how it is a condition for spontaneity, and how we can discriminate the reversible and irreversible process with the help of entropy. With this, we wind up our session. So prepare notes with the help of textbook and submit it. And when you prepare notes, it's better if you compare the topic entropy with spontaneity and understand well how spontaneity and entropy are related. Thank you.